Hi everybody, by popular demand, here is a little summary of the A-B testing guest lecture. Sorry I didn't get a chance to do more of these videos. After I made the first one, it didn't look like viewership was super high, and honestly my main concern was making sure this exam was really good, and it took many days of work, probably like 3 full days. Just, these exams are tricky to write. Anyway, so since this seemed to be the one that was very popular, let's talk about A-B testing. So again, this is not a replacement for the actual A-B testing guest lecture, which is quite good. This is a very abbreviated version, assuming that you've already seen it, kind of summarizing what I thought was most important. So A-B testing, what is it? Well, it's all about determining which of two alternatives is better. It can be generalized to more cases, but mostly it's about two alternatives. And the examples that were given, one was, I have two different color schemes I could use for a website, and I want to use the one that maximizes ad revenue or click-throughs or conversions for sales or whatever in a commercial setting. And so an ideal approach would be, well, I show everyone, all my users or whatever pool of users, version A, and then I go back in time and I show them version B, and then for each person I see which one was better according to some metric, and then I'm good. But of course time travel does not work, and so instead we are forced to do something else. So one thing you might be tempted to do is, well, I'll show users A then B, or B then A, but the problem is then you've already seen both. Your experience of one is colored by the other, and in many cases these A-B tests, they're very subtle in terms of the differences between the two treatments, so that's not really going to work out. And so he says, our guest lecturer, that a carefully designed randomized controlled experiment is really the only reliable way to learn what is actually better. So we gave an example comparing just how hard this problem could be in the context of estimation versus causal inference. So estimation would be, he says this is a relatively easier problem. So if you want to know the difference in birth weight between mothers who are smokers and non-smokers, so looking at their babies after birth, that's an estimation problem. But harder is a causal inference problem, which is, okay, we know that smokers, their babies are generally lighter weight, but if we actually told them to stop smoking, would it actually help with the birth weight? And so to evaluate those two groups, we really need some situation where the only difference is the treatment. Because if we just look at smoker versus non-smoker mothers, there of course could be many other factors like alcohol use or whatever else that might be an issue. And so randomly assigning treatment groups, basically taking a pool of mothers who smoke and then assigning the treatment randomly, that makes our argument stronger. That's when we can start making causal inferences, and that's more data 8, but we saw it in this lecture. This is our one really deep look at causal inference. So when it comes to randomization, he says that adding our own randomization is great. We can now justify all of the chance, all the randomness by design. We chose the randomness. And it's kind of similar, actually, I observed, to what we did with permutation testing. So computing p-values under permutation testing is nice because we know exactly how the randomness arose under really simple assumptions. And the way we computed, say, p-values for, in my hypothesis testing lecture for discussion sections, with permutation testing, it was a stronger way of computing p-values than other techniques such as assuming Gaussian distributions of student ratings and so forth, but that's that other lecture, the hypothesis testing lecture. But I thought it was an interesting connection. So there's 3 important choices that our guest lecturer mentioned. The first was our unit of randomization, and he gave the example of Amazon prices. So we could randomize, for example, by user, so that this user gets a certain price for an air purifier, and this other user gets a different price. And maybe we use that to compare, that could be how we run our randomized experiment. We could do it by product. So instead of a user gets a whole bunch of different prices, maybe I give them all 10% higher or whatever. By product, I guess I was mixing user and product in my previous example. Sorry, user would be, I take a user, I just raise all their prices a little bit. Product would be, I have certain specific products and I'll raise their prices. Category would be, let's raise the price of all toilet paper, because the idea if we only raise one product, toilet paper on Amazon, maybe people just switch because it's fungible. Or you could just change the prices day to day. Now, if our unit of analysis is different from our unit of randomization, we can run into some issues. I'll say a little bit about that in a moment, what that actually means. We also need to decide not just the granularity of our randomization, but who to actually bring into our program. So if we're a website like Amazon, we probably don't want to run an experiment on every single user on the whole site. Or if we, for example, have to pay some amount of money to incentivize users to participate, in that case, obviously, we don't want to enroll everybody. And then lastly, we have to decide how to measure the results. So let's start with, actually, I'll say about randomization, I guess. I thought I had a slide on this. I forgot I didn't. So the unit of randomization, he basically just mentions, let's say we run an experiment where we only have TV ads in San Francisco and Los Angeles, and then we try and measure the outcomes on a per person basis as opposed to a whole market basis. Then you could run into some issues, and he was a little vague about how exactly we would deal with that, but it's something he mentioned. But I guess the big picture, the important point, he's saying there's 3 big choices you have to make, and these last 2 we'll unroll a little more. So let's talk about who to enroll. He says that when we're doing these tests, there's 3 things we care about. The first is the chance of false discovery, which is something you and I know well. This is basically just the p-value, right? The p-value tells us, under the null hypothesis, what's the likelihood we would see what we saw. But he also introduces 2 new terms we had not seen previously in the class. We saw lift, which is how much the result is improved, and I'll give an example in a moment. And power is how likely you are to discover an effect with that amount of lift. And so he gives some examples. So let's say we're talking about, I don't know, well, I'll be vague like the one here. So if the treatment, the thing we're doing, whatever it is, telling mothers not to smoke, raising the prices, if the treatment has no effect, the chance of false discovery is at most 5%. That's what this is, the chance of false discovery part. I'll call this number 1. Hypothesis testing is how we do that, and we already know about this in this class. And what was a little new in the middle of this lecture was the idea that if we wanted to make a statement like, if the treatment has at least 20% lift, the chance of detecting it is 80%. That he calls, the way he addresses that is something he calls a sample size plan, which is just a fancy way of saying how many users or individuals or entities we need to include in our experiment. And he says there exists, and he gave no background on how it works, but he said there exists a function where you give it, effectively, this is my lift here, 20%, this is my chance of false discovery, and this is my power, how likely I want to be able to see this 20% lift. Those 3 numbers together can be dropped into this function, which I honestly don't know how it works. This is not something I've personally learned about. And you will get back 3,840. And so that function exists. And essentially, when he says, in trying to address this question of who to enroll, part of the question, if you're doing this in the real world, is you decide in advance what chance of false discovery, lift, and power you want. And that tells you how many folks you need in order to attain the goals you have. Okay, that's pretty cool. I think it's fairly straightforward. Now, one subtle issue is that test I described, it doesn't actually take the lift as an input, but instead it takes a P1 and P2 value. And P1 is basically the chance without the treatment that some event occurs, and P2 is the chance with the treatment that some event occurs, at least in this specific example. Okay, so now that we understand the idea of chance of false discovery, lift, and power, we can now discuss a little bit more about this question of who to enroll. So he gave an example, basically saying, let's suppose we're trying to get a 20% lift. That is, go from a 20% conversion rate to a 25% conversion rate. Again, because he's in this commercial space, he thinks about conversion rates. Over here, we have a 40% conversion rate, and we want to get up to a 50% conversion rate, which is also a 20% lift. Well, it turns out that this test, this black box function, we don't know how it works. Well, when these p values here are larger, you need fewer samples. So in other words, if we already have a group that is predisposed to have a higher conversion rate, we could do experiments on them with fewer users. You only need 770 versus 2,200 users. Now in this case, this brings up an interesting tension he describes as internal versus external validity. So the choices about who you enroll, they may improve the internal validity, that lets you get a really good understanding of your enrolled subjects, but it may mean your external validity doesn't work well. And so the example he's giving here is that on some website, users who have 2 items in their shopping cart are more likely to actually check out. But the experiment you're running, maybe about displaying some certain thing on the website, prompting for a discount code, who knows what, it may not actually apply to that broader pool of people. So it may have great internal validity for this high conversion rate group, but poor external validity for everyone. Okay, and so the tension there with who to enroll is that we can have fewer samples if we're taking specific subsets of our users, but it may affect the validity of our conclusions. And the last thing he talked about in some detail was how we picked a metric. So we have to decide, for example, how do we know that this treatment was better than the other? What's our number? With the shopping example, he had a very simple metric, which was the number of, or the percentage of people who actually checked out and paid, who had stuff in their cart. But this metric could be complicated to discuss. So an example I like that I'm bringing in personally is the time you spend on, that your users spend on your website. So you're Facebook and you're using time spent on Facebook as my metric. Well, there's a few reasons that might be bad. So if you increase it. So you might think, great, more people using the website for more time, wonderful. But maybe your site is just terrible and people are spending a lot of time trying to figure anything out. And maybe that means in the short term you get more engagement, but in the long term people leave. Or another side effect, and this is now divorced from some profit motive, is it may be harmful for everybody to be using your thing all the time. So for example, Snapchat, right? So Snapchat, if you're not familiar, it's a messaging app, and they have a feature known as a snap streak. Doesn't really matter too much what it is, but I would bet you that they used A/B testing at some point to experiment with snap streaks and try and get users to take advantage of this feature that keeps them talking. However, the net effect is that people waste a lot of time trying to maintain snap streaks, and I personally find it a little gross, but I don't know. That's just my personal opinion, and essentially it just wastes human time on Snapchat doing things that nobody cares about. Not even the people who are getting snap streaks. And a suggestion by the guest speaker to close this out is he was saying you may have many different metrics that you want to consider, whatever they may be, and he suggested strongly that you want to pick, if you can, a key performance indicator. And if you were to try and measure multiple things, like I want to measure time spent on the website, I want to measure conversion rate, I want to measure reviews on Yelp, I don't know what. It can be very challenging, but he didn't go into any detail at all, so obviously way out of scope for us. But he says you can go read about the multiple comparisons problem if you want to know more. It's a good thing to be aware of if you go into this space. So if you end up using data science skills for purposes that involve A/B testing, a good thing to learn about in the future. All right. He ended with a pretty interesting topic, which was new to me. I hadn't actually thought about this very much before. So this is sequential testing, and this is where basically we're running, or sequential monitoring, he describes it. I'm actually going to add this to the header. Oh, it's me. Okay, so sequential monitoring. Okay, good. So he basically says, how do we know when to stop an A/B test? So here we're actually doing 4 different things at once, not 2. But we want to know which version of the website is best for maximizing conversion rate. So this is from a commercial tool that I've never used. You can read about it here. But looking at this, the orange, if we look at the end of the experiment, the orange one seems to have clearly the best conversion rate. So some questions that pop up that are very natural, kind of like if you've ever done stock trading, which is like, oh, well, could we have stopped earlier? Was there some better place to get out and stop the experiment earlier? Or should we have kept waiting? Like maybe one of these is going to come up from behind. How do we deal with that challenging problem? So he discusses a few really interesting experiments that you can do computationally, and says basically, well, let's consider the null hypothesis. So the null hypothesis is that neither choice is better. And he gives an example where he says, let's flip a coin every day and I get a point for heads and you get a point for tails. And talks about the distribution of possible scores over time. And one of the things he mentions is that of such experiments, 15 out of 100 experiments where you run such a thing, you'll see that one player is ahead 357 out of 365 days. So if, as a class, we had you guys play this game with each other in pairs, there would be way more super lopsided games than you might imagine. And in fact, he shows this nice distribution that if we did this with tons and tons of experiments, roughly speaking, what it looks like. And it is in truth symmetric, but this is a computational experiment, so it doesn't actually quite converge to the symmetric version. But it's actually more likely that any given player is going to have a very skewed game. Like the most likely situation, in fact, is that one user is going to get ahead, or one player is going to get ahead and stay ahead like almost the entire year. And it's relatively uncommon that we have these back and forth. I'm ahead for a little while, you're ahead. And the reason he brings this up is our intuition about the long run behavior of random fluctuation is not super great. And so where it relates back to our A/B tests here is if I'm doing an A/B test and A pulls ahead for several days in a row, like I deploy a new thing, I'm like, hey guys, I have a beautiful website design. I put it out there, we A/B test it, and in the first 14 days, it's just crushing it. It's like ahead every single day. That doesn't necessarily mean your design is better, because you may just be suffering from the coin flip game problem. So this brings us to an approach that he specifically contraindicated as a bad idea, which is what you really should not do if you're using this commercial tool, is look at this website every day, F5 in your browser, and just keep looking and wait until one of the 4 variations exceeds well, in this case, they have a baseline. But what you should not do is just look every day, refreshing until one of these exceeds 95%. Why 95%? Well, each of these numbers, you can think of it as 1 minus p. So you could say, at this point, finally, I've beaten the 5% confidence interval or 95% confidence interval I really care about. So why is that approach such a problem? Well, it goes back to the coin flip idea he was discussing. I thought this was a particularly cool figure, basically that here's a bunch of potential outcomes of that game, and here they're plotting not the score like before. I didn't show the plot, but here the y-axis is not the score, but instead the p-value of that particular game. So we'll see that only a relatively small number of games actually end up, after 215 flips, having some really unlikely occurrence. In fact, 5% of the games you play will, at 215 flips, be in the below the 5% line. So there's no really big surprise here. That's like, all right, great. That's just the definition of a p-value. But the other figure he showed, which is a little different, which I thought was really neat, is that let's suppose after every single flip you check to see, is this game going weirdly? And what he showed was that, well, the games, they wander around the p-value where you are, but this green dot here indicates that this game, it was pretty normal, but then there was a moment where it entered a state that was highly unlikely, that after 220 flips you would see this particular thing, this particular event. And he said that 35% of the games that you play, after 437 flips, if you check every single time for anomalousness, you'll fall below this line at some point. So in other words, p-value, no surprise that 95% of our trajectories at this moment are above the 5% line. If instead we check every single moment in time, hey look, we're below that line 35% of the time if we check every time. And in fact, if we just keep playing over and over, right, after thousands or tens of thousands of flips, all of these trajectories will eventually cross this line at some point. So that's kind of interesting. So how do we correct for this sequential observation? Well, this part, he gave more of a high-level picture, but the neat way of thinking about it is we have to take this into account. We have to take into account that we're going to look many times, and so he says, instead of thinking of our test statistic, say number of heads minus number of tails or number of conversions on our website, we have to realize that we're taking a sequence of test statistics of which we are taking the maximum. That is, I'm looking every single day and I'm seeing what's the p-value today, what's the p-value today, what's the p-value today, over and over. And so in effect, I'm measuring at each time whether anybody has gone wild, so to speak, that we've ever crossed this point. And so if we realize that we're taking the max of many test statistics, instead then what we'll do to address this is we'll decide in advance the maximum number of trials we're going to run, the maximum sample size, and the interval. So maybe I'm going to flip 1,000 coins and I'm only going to look every 100 coins. Or I'm going to do an A/B test on 1,000 users and I'm only going to look after every 100 tests. So I have some number of users using the site, and then every time we hit 100 new users using getting the A/B test, then we'll look. So basically we'll only see this at intervals. And then what we'll do is, so we have all these test statistics, T100, T200, T300, T1000, and then what we'll do is we will recognize that effectively, if we're thinking about the max over time, then our test statistics that we're actually using to make decisions are T100, the max of T100 and T100, or sorry, T100 and T200, the max of T100, T200, and T300, and so forth, which our guest lecturer called lowercase T100, and so forth. He also talked about rescaling to correct for the fact that the variances are different. He didn't say much about that in lecture. I won't say anything about it now. And then he finally says, now that we have these special test statistics that are actually maxes of these individual like snapshot test statistics, then we would simulate the observation probability of these maxes under the null hypothesis, and therefore we get more meaningful p-values. Now this was a fairly challenging notion to fully digest. We had no homework on it, no discussions about it, so I'm not going to go obviously on the final into great detail with this. And if it didn't quite make sense, I think this figure might help a little. So here, he basically says, naively, if we look at some sequence of coin flips, we might say, we looked over and over and over and we said, oh, there's only a 2.9% chance that we've seen that this is a false discovery. But if I instead take into account the fact that I was computing the max of a bunch of observations, the particular observation that I might observe is only 5.4% likely to be a false discovery. In other words, if we take into account for some specific observation the fact that we're taking a bunch of maxes, then the p-value will be somewhat larger. And maybe the really interesting thing is, looking at the actual figure, is this. So if we were trying to imagine the distribution of number of heads minus number of tails after doing 1,000 flips, it would naturally be centered at 0. However, here, this special observation, T star 1000, which is the max of the previous 1000 observations. I don't know why I used a capital here, because this is the lowercase version, but hey. But this right here, you see it's centered above 0. And that basically is just saying, if you play the coin flip game over and over, and you keep measuring over and over, and you keep measuring over and over the difference in computing the max of all of those observations, that will be centered above 0. And so, in effect, if you want to know whether or not the coin game is fair, if you're taking a bunch of maxes, you need to take into account that those maxes will be centered above 0 and not at 0. So that's the short version of this more complicated slide. And I know that's probably a little hard to digest, but I hope you found it interesting. And that pretty much wrapped up the A/B testing lecture, and basically the message there, okay? So, absent the kind of technical details there that I don't know that it did a great job re-explaining, the key point was, if you are doing an A/B test like this, and you refresh every day, and you look at that p-value, you're doing something that's a little dangerous, and that you really need to be taking into account your observation process itself in order to compute a more reasonable p-value. Okay? But that's something that if you go and learn and work in this world, doing your own experiments in science or in industry or whatever, you'll get into the stuff. And this lecture, of course, was just a peek at that. All right, hope you found this video useful, and that's that.